Hello everybody, welcome to today's class on Introduction to Energy Balances. We have looked at some of the fundamental aspects for performing energy balance calculations in open and closed systems and also learnt about thermodynamic tables in the previous few lectures. Today we will perform some calculations and problems as a tutorial session so that we get completely familiarized with the concepts that we have learnt and we would feel comfortable solving the problems which would be given in terms of energy balances. Let us first start with the first problem for the tutorials. Since blood is refrigerated for storage, it is warmed before contact with a patient to prevent hypothermia. Calculate the rate of heat required to continuously warm 10 liters per minute of blood from 30 degrees Celsius to 37 degrees Celsius using an electric heater. A stirrer adds work to the system at a rate of 0.5 kilowatts. Assume the heat capacity of blood is a constant at 4.185 joules per gram degree Celsius. The density of blood is 1 gram per ml. Working volume of the tank is 1 liter. So, we have been given all the information that we need to perform the energy balances for this problem. Let us start solving the problem with the flow chart. So, here we have blood flowing at 10 liters per minute. So, you also have been given that work is done on the system in the form of a stirrer which is given as the shaft work Ws is 0.5 kilowatts. Would this work be positive or negative? According to our convention, we have assumed that work done by the system is positive and work done on the system is negative. If that is going to be the case, here work is done on the system, which means this would be considered to be negative work. So, Ws is given as negative 0.5 kilowatts. Now, we also know that heat is supplied to the system in the form of Q dot, which is the heat, and then we can calculate this Q dot using our general energy balance equation for an open system. For an open system, the general energy balance equation is delta H dot plus delta Ek dot plus delta Ep dot equals Q dot minus Ws dot. So, in this equation we can ignore kinetic and potential energies because there is actually no change in height which has been given to us, or there is also no change in the velocity of the blood which is flowing. Because of this, the equation simplifies to Q dot equals delta H dot plus Ws dot. So, now we need to calculate delta H dot. Ws dot is already given to us. So, Ws dot can be entered as minus 0.5. So, the value for Q dot would be delta H dot minus 0.5 kilowatts. So, if we can calculate delta H dot in terms of kilowatts, we can substitute this value here and find the value for heat which needs to be supplied. So, what would be delta H dot? So, we have been given the Cp value for blood. So, using this we know that delta H dot can be calculated as m dot integral Cp dt from T initial to T final. So, here m dot would be 10 liters per minute times 1000 grams per liter. So, this would give us grams per minute, and if we need to convert this to grams per second, we would multiply this by 1 minute contains 60 seconds, and then this is the m dot value plus integral of Cp has been given as 4.185 dt with temperature going from 30 degrees Celsius to 37 degrees Celsius. So, this value can be calculated as 4.882 kilowatts. So, delta H dot is equal to 4.882 kilowatts. As we have Q dot equals delta H dot minus 0.5 kilowatts. So, we can substitute the value for delta H dot here, which is 4.882 minus 0.5, giving you a value of 4.382 kilowatts. So, the heat that needs to be added to the system would be 4.382 kilowatts. So, this was a simple energy balance problem for an open system. Let us perform more of these example problems to get us familiarized with performing energy balances. Here is the second system. Here again you have an open system, however, here we will be using steam tables instead of using m integral Cp dt. So, let us look at the question. To sterilize a fermenter, two streams of water are fed. Feed 1 is 120 kilograms per minute at 30 degrees Celsius and feed 2 is 175 kilograms per minute at 65 degrees Celsius. The pressure inside the fermenter is 17 bar absolute. The exiting steam leaves the fermenter through a 6 centimeter inner diameter pipe. Calculate the required heat input to the fermenter in terms of kilojoules per minute if the steam leaving is saturated at the fermenter pressure. You can neglect kinetic energies of the liquid inlet stream. If you read the question carefully, we have all the information about the streams which are coming in and leaving the system. We know that we have two feeds, one at 120 kilograms per minute and the other at 175 kilograms per minute. We also know the temperature at which they are coming and their states. We also have information about the pressure inside the fermenter and the exiting steam's state. We have been told that exiting steam is saturated and we also know that the exiting steam is leaving through a 6 centimeter inner diameter pipe. The problem gives us that we have to ignore kinetic energies of the inlet stream, which means we would have to account for the kinetic energies of the exit stream. So, using this information, let us try to solve this problem. So, here is the flow chart which describes the process. We have 120 kilograms of water liquid at 30 degrees Celsius and 175 kilograms of water liquid at 65 degrees Celsius coming in. Heat is supplied to the system and we have 295 kilograms of water vapor leaving as saturated steam at 17 bar. So, based on all this information, we will have to perform energy balance calculations. So, this being an open system, the general energy balance equation would be delta H dot plus delta E k dot plus delta E p dot equals Q dot minus W s dot. Now, we cannot ignore the kinetic energy term because we have been told that only the inlet kinetic energies can be ignored. So, we have to calculate the outlet kinetic energies. So, this term would exist. Obviously, delta H dot will exist because you have change in enthalpy due to phase change which is happening and also due to temperature change which is happening. So, we can ignore potential energy changes because there is no change in position or height of the streams which has been given to us. So, we can assume that this is negligible and it is 0. Q dot and W s dot have to be looked at. So, Q dot is the heat which is supplied for the change in enthalpy and the kinetic energy. W s dot would go to 0 because there are no moving parts, you do not have any shaft or piston which is there. So, which means W s dot can also go to 0. So, the equation simplifies to Q dot equals delta H dot plus delta E k dot. So, let us first calculate delta H dot. For calculating delta H dot, what do we need? We need information about the inlet enthalpies and the outlet enthalpies. So, this we can identify by using steam tables. So, please go back and refer to steam tables from one of the textbooks, or if you have access to some other steam tables, please refer to the steam tables which you have to identify the enthalpies for the inlet stream, which is liquid water at 30 degrees Celsius and liquid water at 65 degrees Celsius. You would also have to identify the enthalpy, specific enthalpy for saturated vapor at 17 bar, which is your exit conditions. Using the steam tables, we can identify the specific enthalpy for water liquid at 30 degrees Celsius is equal to 125.7 kilojoules per kilogram. Similarly, the specific enthalpy for water liquid at 65 degrees Celsius is equal to 271.9 kilojoules per kilogram. So, looking at the saturated steam tables, we would be able to get the specific enthalpy value for saturated vapor which is water at 17 bar as 2793.4 kilojoules per kilogram, and the temperature is 204 degrees Celsius. So, having these values, we can calculate delta H dot. Delta H dot is equal to sigma of outlet streams m dot H cap minus sigma of inlet streams m dot H cap. So, this would be 295 times 2793.4 minus 120 times 125.7 plus 175 times 271.9. So, this value would be delta H dot equals 7.61 times 10 power 5 kilojoules per minute. So, this gives you the change in enthalpy for the process. So, the next term we need to calculate is the change in kinetic energy. As we are assuming the kinetic energy of the inlet streams are 0, calculating the kinetic energy of the exit stream will give us the total change in kinetic energy. So, for calculating the kinetic energy of the exit stream, we need to calculate the velocity. So, for that we need to be able to calculate the volumetric flow rate divided by cross sectional area. So, first thing is for us to identify volumetric flow rate. How can we convert the mass flow rate that we have into volumetric flow rate? The stream tables gives us information not just about internal energy and enthalpy, it also gives us specific volume. Using specific volume, we can convert the mass flow rate which we have into volumetric flow rate. So, let us first identify the specific volume for the exit stream. For specific volume for the exit stream would be equal to 0.1166 meter cube per kilogram. So, this is the specific volume for the exit stream based on the stream tables. Now, we need to multiply this specific volume with the mass to get the volumetric flow rate. So, the volumetric flow rate would be equal to 0.1166 times 295. So, this would give us volumetric flow rate in terms of meter cubes per minute. Now, we have to divide this volumetric flow rate by cross sectional area. So, cross sectional area A can be calculated using the inner diameter which has been given. So, cross sectional area is pi r squared, which would be pi times 3 squared, where 3 is the inner radius of the pipe. So, this would give us the area, cross sectional area in centimeter cube, and converting it into meter cube, we would have to divide it by 10 power 4. So, this gives us a value of 2.83 times 10 power minus 3 meter squared. So, this is the cross sectional area. So, we can get velocity as volumetric flow rate divided by cross sectional area, which gives us 295 times 0.1166 meter cube per minute divided by 2.83 times 10 power minus 3 meter squared, and we would also like to convert this minutes to seconds. So, we divide it by a 60. So, giving us the velocity as 202 meters per second. So, this is the velocity of the exit stream. Now that we have the velocity, we can calculate kinetic energy, which is delta E k dot as half m v squared. Here m dot is 295 kilograms per minute, and we have velocity in terms of meters per second given as 202. So, this kilogram meter squared per second squared will be converted to kilojoules because that is the derived units. So, we get a value of 6.02 times 10 power 3 kilojoules per minute. So, substituting this back into the equation for heat, we get Q dot equals delta H dot plus delta E K dot, which is 7.61 times 10 power 5 plus 6.02 times 10 power 3, giving us Q dot equals 7.67 times 10 power 5 kilojoules per minute. So, this is the heat which needs to be supplied to the system. What I want you to understand from the calculations which we did is, even while we ignored the kinetic energy of the inlet streams and accounted only for the kinetic energy of the exit streams, we got a value which was 1/100th the value which you would have gotten for the change in enthalpy. So, the change in enthalpy was in the order of 10 power 5, whereas the change in kinetic energy was in the order of 10 power 3. This indicates that if for a thermodynamic process where there is change in temperature or phase, the change in specific enthalpy or change in enthalpy is a lot more significant than change in kinetic energy. That is why in many cases we tend to ignore change in kinetic energy while we perform calculations. So, here we have been able to calculate the total change in heat even by accounting kinetic energy, which accounted only for about 1% of the final answer. Now that we have a clear understanding of this, let us move on to the next tutorial problem. Until this point, we have been performing energy balance calculations only. In this problem, we will look at simultaneous material and energy balances to obtain the values which we are looking for. The problem statement states saturated steam at 1 atmosphere is discharged from a turbine at a rate of 1150 kilograms per hour. Superheated steam at 300 degrees Celsius and 1 atmosphere is needed as a feed to a heat exchanger. To produce it, the turbine discharge stream is mixed with superheated steam available from a second source at 40 degrees Celsius and 1 atmosphere. The mixing unit operates adiabatically. Calculate the amount of superheated steam at 300 degrees Celsius produced and the required volumetric flow rate of the 400 degrees Celsius steam. So, here unlike the previous problems which we looked at for energy balances, we have not been asked to calculate change in enthalpy or heat. However, we have been asked to calculate the mass of superheated steam produced and the volumetric flow rate of superheated steam which is required to be fed. So, these are usually terms which we calculate from material balances. However, if you were to write material balances for this problem, you would find that the degree of freedom is not equal to 0. So, to solve this problem, we also need to write the energy balance equation. Let us see how we go about solving such a problem. Here is the flow chart which describes the process. You have the turbine discharge coming in at 1150 kilograms per hour. The conditions for that are given. You also have a 400 degrees Celsius superheated steam being sent to the mixer, and the final outlet stream is the mixed steam containing both these streams, and this is a superheated steam at 300 degrees Celsius and 1 atmosphere. For performing calculations, the values for enthalpies can be obtained only from steam tables. So, let us look at how this problem would be. What are the material balances that we can write? So, here the only material balance we can write would be the total material balance, because you have only one component and it is a mixer. So, the total material balance for this problem would be 1150 plus m1 dot equals to m2 dot, where 1150 is the mass of water vapor entering as turbine discharge, and m1 dot is the mass of superheated steam being fed to the mixer, and m2 dot is the mass of superheated steam which is produced. So, this one equation and you have two unknowns. So, this is why you have a degree of freedom which is greater than 0. So, here you would have 1 degree of freedom. So, you cannot calculate both these values using only material balance. So, here we would use energy balance to the rescue. So, the energy balance equation for this open system would be delta H dot plus delta E k dot plus delta E p dot equals Q dot minus W s dot. Considering that this system does not have any acceleration or change in position, we can ignore the kinetic and potential energy changes. So, these two terms go to 0. As we do not have any moving parts in the system, Ws also goes to 0. In addition to this, the problem statement tells us that the process is adiabatic, which means there is no energy supplied from the system to the system from the surroundings in the form of heat. So, there is no heat exchange between the system and surroundings, meaning Q dot is also equal to 0. So, you end up with an equation which is delta H dot equals 0. Now, we need to calculate delta H dot in terms of the mass flow rates which we have. That would help us with the second equation, which can be used along with the material balance equation to get the mass flow rates of the inlet and the outlet streams. Let us try doing that. So, delta H dot would be equal to sigma of the outlet streams m I dot H I cap minus sigma of the inlet streams m I dot H I cap. So, the outlet streams are m2 dot times, let us call this H2 cap, minus m1 dot times H1 cap plus let us call that m0 dot H0 cap. So, where m0 dot is 1150 and H0 dot is the enthalpy associated with the inlet stream. So, looking up the steam tables, we can identify these values. So, enthalpy H cap for specific enthalpy for water vapor which is saturated at 100 degrees Celsius is equal to 2676 kilojoules per kilogram. Specific enthalpy of water vapor at 400 degrees Celsius. So, this is the superheated steam would be 3278 kilojoules per kilogram. Specific enthalpy of water vapor which is superheated at 300 degrees Celsius is 3074 kilojoules per kilogram. So, substituting these values here, we get delta H dot equals 3074 times m2 dot minus 3278 m1 dot minus 2676 times 1150. Substituting this value of H dot into the equation we had, you would have delta H dot equals 0, which means the equation we got would become 1150 times 2676 plus m1 dot times 3278 equals m2 dot times 3074. So, this equation is the second equation which again has m1 and m2. Using the material balance and this equation, we can solve them simultaneously to get m1 dot and m2 dot. So, m1 dot from here would be 2240 kilograms per hour and m2 dot would be 3390 kilograms per hour. So, m2 dot is the mass of the final superheated steam which is produced from the mixer. So, 3390 kilograms per hour of superheated steam at 300 degrees Celsius is produced from this mixer. We have also been asked to calculate the volumetric flow rate of the superheated steam at 400 degrees Celsius which needs to be supplied to the mixer. So, we have the mass flow rate, we can again convert this to the volumetric flow rate using the specific volume data which is available in the steam tables. The specific volume data for this particular condition is 3.11 meter cube per kilogram. So, using the specific volume, we can calculate the volumetric flow rate as V equals mass flow rate which is 2240 times the specific volume which is 3.11, giving volumetric flow rate as 6980 meter cube per hour. So, this would be the volumetric flow rate. So, with that we come to the conclusion of basic introductions related to energy balances. In the subsequent classes we will look at different types of energy balances. So, whatever we have looked at till now are for chemical processes. We will also look at mechanical processes where we have to perform mechanical energy balances, and later on we will move on to performing energy balance calculations on more complicated systems. Until the next class, thank you and goodbye.